right, so as we just said, we've got our quiz tomorrow. This is going to cover section 6.1 through 6.3 only. This is on graphing sine and cosine 6.1, graphing the other trig functions 6.2, and then 6.3.
The inverses.
Again?
The inverses.
Yeah, the inverse trig functions out of 6.3. So we'll do those three things, and maybe you have some questions on those you'd like to look at before we get going. I think we'll probably learn more if we do those first.
Yeah, it's been a while since I've done a tan, so I was going over how to draw tangents again, and I'll
Okay.
give you some help more on the finding the asymptotes on the tans.
Okay, yeah.
I guess let me give you a specific question, like
Okay.
2a, which is 2 tan parentheses 4x minus 32.
Two tangent what?
Parentheses.
Oh, 4x minus 32, okay.
Yeah.
Okay. I just guess that,
Yes.
with the 6.2, I guess. So suppose I want to sketch this. When you make a sketch of any of these things that have asymptotes, I want you to sketch the asymptotes. So those are very important. And then for tangent, you also want to sketch that point where it crosses the middle. So this one, if you think of this as A is always the number that multiplies the trig function. B is the number that multiplies X. C is the number that's subtracted in here, and then if you put a plus 0 on here, whatever's added on the end is D. So there's A, B, C, D. You can do the same 5 steps you did with sine and cosine, except that you don't call it amplitude because it goes off to plus or minus infinity. You just call it stretching factor or something like that. And the period changes. The period, instead of being 2 pi over b, is pi over b because the original tangent function is pi periodic, whereas sine and cosine were 2 pi periodic. So if I want to sketch this, I just go through the same 4 steps and keep those 2 things in mind. From the 4 letters, I get 5 properties. One, I like to do the shift first because that's where the origin moves to. So we'll say the phase shift or horizontal shift, whichever one you like to call it. Just like sine and cosine is C over B, right? So it's whatever subtracted here plus 32 over 4 is 8. There's the horizontal shift. Now I've also got a vertical shift sometimes. Usually we only do vertical shift for sine and cosine just because most applications don't require it for the other 4 trig functions. So a good chance you'll get 0 on the test too, but I don't promise. So is there a vertical shift here? Sure enough, there's not. For this one, we'll say, suppose it says the vertical shift is D, that's 0. There's no vertical shift. Now what you can do is you can start your sketch, right? You can go over to the shift point. 1, 2, 3, 4, 5, 6, 7, 8, 0. And we know that the tangent, if we just sketch the tangent function without stretching and shifting, it looks like this. It goes through the origin, right? These were the important points. 0, 0, 45 degrees of pi over 4, 1. And minus pi over 4, minus 1. And then the asymptotes were pi over 2 and minus pi over 2, and then it's pi periodic. And so there's another asymptote of 3 pi over 2 and so forth. And what happens is this crosses the axis at multiples of pi, 0, pi, 2 pi, 3 pi. That's where the tangent crosses the x-axis. And then it has asymptotes at odd multiples of pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, minus pi over 2, minus 3 pi over 2, and so on. Now this was the tangent function. When we do these shifting and stretching techniques, what it does is it is the shift, or the translation they call it sometimes, is of the origin. Well, the tangent went through the origin, so it's going to go through the shift point here. It's going to go right through there. Now, we also have to check if it's flipped, and I have to not draw it up through there like the normal tangent. I have to flip it upside down and go down through there. So this is an unflipped tangent. I'll go ahead and start that through there. But you start there, and then you find the shift point, and then from the shift point, A0, use the rest of the letters. The stretch factor, since it's not a wave, is absolute value of A, just like the amplitude for sine and cosine is 2. So that's going to stretch it twice as tall, twice as far from the x-axis. And then the period, since it's, the tangent function is pi periodic, the period is pi over b, not 2 pi over b. Remember that in the test. This is pi over 4. And so that's steps 3 and step 4. And then step 5 is, do you flip it? No, there's no flip because it is positive. All right, so I did draw that up through there correctly. Now what I have to do with tangent, this is the way most people draw it, is they'll go from this shift point and then they'll go half the period to the right. The period is pi over 4, so I'll go pi over 8. That's less than 1, boy, that's about 3/8 of a unit. It's not very far. All right, so this would be 8 plus pi over 8, half the period to the right, and half the period to the left. 8 minus pi over 8. And I draw asymptotes there. I use my colored chalk. So that's what we usually do for tangent is we'll find the shift point, go half a period to the left, half a period to the right. Then if it's not flipped, we'll just make a curve that goes up through the shift point. If it flips, we'll make a curve that goes down through the shift point. And it looks about like that. Get to one period of our function, and then it just repeats over and over, right? You go another, I'm surprised this problem is such poor numbers. It's such a tiny squeeze way out there. But then it repeats after that. This would be 8 plus twice pi over, plus another period of pi over 4, which I guess 8 plus pi over 8 plus a period is pi over 4. So it'd be 8 plus 3/8 pi. Those are not very good numbers, but you could make another asymptote and draw it through the middle here. And since the period is pi over 4, this is 8, this is 8 plus pi over 4. So you can draw it exactly like that, and then you can check it in your calculator to see if it looks like that, but the calculator won't give you the exact numbers. You kind of have to know them and then plug in those check marks and see if it seems to go through them.
Right, so I guess my question is, like, so you see where we're drawing the first asymptotes, 8
Yeah.
plus pi over 8. Where do you get pi over 8? I thought the period was pi over 4.
Yeah, I go half the period each side, so between the asymptotes is 1 period. Yeah, that's the tricky ones, is the tangent and cotangent. It's got a different period and you have to figure out where the asymptotes are. All right, so if it says draw 1 complete period, you draw this one. If it says draw 2 complete periods, you draw this one. There is one more thing I left out here. This is not real critical. But if you want to see, well, is it real stretched out or is it real squashed like that? What you can do is plot a couple points and halfway between here and the asymptote. So it'll be 8 plus pi over 16, halfway in between. You would be 1 unit up if it's unstretched. But the stretching factor is 2. I didn't take that into account, so it goes up to 2. And then on the left here, similarly, at 8 minus quarter of the period, pi over 16, that'd be a minus 2. The stretching factor downward. So you can get an idea how to sketch it from that. If I made one this complicated, I probably wouldn't expect those points, but if I make a simpler one, I might like you to sketch those. But if you can sketch, sketch this where the origin moves, sketch the asymptotes and these 2 important points, that's all I'm gonna expect, even on simple set of numbers. Anything else that you want to look at? Okay. I should be good at this stuff. I want to hazard one more guess of something that's hard here. Suppose I asked you to do this one. Evaluate exactly, maybe I should do the one out of the problems there. I just want to do a couple of these in practice for tomorrow on inverse trig functions, since we didn't ask any on that. Maybe this will jog your memory of another one you want to see too. What is the exact value of the arc cosine of minus square root 3/2? How would I find that? You get that question. You have to be able to evaluate these things by hand when they come from special angles. I recognize minus square root 3/2 comes from 1. So I know I can do this exactly. How can I? You'll probably get one of these tomorrow. Aren't you glad you came to class with people who didn't come? Won't be this exact one. Remember, you can solve these on the unit circle when they come from a special angle. If they don't, then you just use your calculator, right? So what I do is I say, we want, it's the reverse question. You're asking what angle? The angle depends on whether it's which inverse trig function. It's for cosine, it's an angle between 0 and pi, right? What angle between 0 and pi has this cosine? That'll be the arc cosine, right? Well, cosine is the x coordinate. So I put x equals minus square root 3/2. Here's the vertical line of all x coordinates minus 0.87 square root 3/2. I observe that there's exactly 2 intersection points. That means there's exactly 2 terminal rays. There, and there's only one answer to this, though. It goes to one of those 2 terminal rays. It's the unique angle between 0 and pi that goes to one of those. Well, it can't be that way. It's negative. Can't be all the way around here. That's more than pi, right? Pi is right here. It must be this one right here. So this is the arc cosine. What is its value? And that was not. Well, let's see. I dropped the perpendicular. I notice this goes to minus square root 3/2. So the length of this side here is plus square root 3/2. This side is 1 because we're doing it on the unit circle. That forces this side to be a half and a 30, 60, 90 triangle. That angle is pi/6, 30 degrees. So this one, theta, must be pi less pi/6. Well, 1 pi minus a 6 pi is 5/6 pi, right? Minus a 6 is 5/6. 1 pi minus 5, 1 minus pi 6 is 5/6 pi. So the answer to this one is 5 pi/6 exactly. And if you get the nice calculator and learn how to use it, it's harder to use. But I recommend it if you're going on to calculus. It will help you immensely in calculus. Help you a little here, a lot in calculus. The calculator will verify that's 5 pi/6. But on the exam, I want you to show me the unit circle or something to show me you can figure it from that. All right, let's try this one. What's the arc sine? -1. How about that? Is -1 a sine of a special angle? Sure it is, yeah. So how do I find the arc sine? I say what angle between minus pi/2 and pi/2? Right? That's the range of the arc sine. Has sine equal to this. Sine theta equal -1. That's the arc sine question. How do I figure that? Unit circle, right? Well, the unit circle is extremely useful. That's why it's on the review sheet for this course. Makes this cluttered. So now I go to the unit circle. Camera's on screen. And I say arc sine we want sine theta equal -1, but sine theta is the y coordinate. So we draw all points in the plane whose y coordinate is -1. There's only one point on the unit circle with that y coordinate. So there's only one terminal there, right here. So what's the angle? It's not that one. We have to have an angle between -pi/2 and pi/2. It must be this one. -pi/2. Right? The answer then is that arc sine of -1 is -pi/2. You do that for me tomorrow?
So,
Okay. You guys all get a perfect score. All right, so how about this one? This class is keeping. How about, let's do this one. C, this is the hard one. This is the one that I wanted to make sure I reviewed today. Probably nobody wanted to ask it, not doing your homework on time. What is the tangent of the arc cosine of -1/2? What do you think that is? Not -1/2. Let's do this one. Cosine of the arc sine of x over x plus 1. I'll pull one out of the homework here. Did you try this one? How do you do that? It's a special case that'll come up again in bi-chain calculus if you don't remember. When you have a trig function of an inverse trig function, it doesn't matter what this is, as long as this is defined, you can find this exactly. So I mean, over there, we had to get an angle that came, a number that came from a special angle in order to evaluate my head exactly. Otherwise, we had to use calculator approximation. But this one, you can always do it, provided this is a number for which the arc sine is defined. This one always works. So what you do is this. It's a three-step method, we said, right? You let theta be the inverse trig function you see. Arc sine x over x plus 1, right? That's the first step. I guess I get rid of this. Then, this equivalently by taking the sine of both sides, says sine theta on the left. And remember, sine always undoes the arc sine whenever it's defined. So you get x over x plus 1. The other way is not always true. The arc sine of the sine only gives you the right answer if you're in certain. If you're on that portion of the trig function that inverts it. We're going to get back to that. Sine theta equals x over x plus 1 by taking the sine of both sides. And so you draw a right triangle that makes that so. That's the first step. You draw a right triangle that has the inverse trig function in it, theta. Well, that means that the sine, the opposite of the hypotenuse, has to be x over x plus 1. We'll just put x here and x plus 1 here. Sine of theta is x over x plus 1. Theta is the arc sine of x over x plus 1. Step 2 is use the Pythagorean theorem to complete the triangle. What's this side? Good geometry, right? Root of hypotenuse squared minus length squared, right? I often give lectures and people know the answers when I start, but by the time I get halfway through, they think I'm trying to trick them. I won't answer. All right. Either that or I befuddle them along the way somewhere, right? Okay. Square root x plus 1 squared minus x squared. What is that? It reduces, right? This is square root of x squared plus 2x plus 1. If you FOIL this out, it's not x squared plus 1 squared. It's x squared plus 2x plus 1. And then minus x squared. Oh, they cancel. This side is the square root of 2x plus 1. That's what this side is. Right? Square root of the hypotenuse squared minus the leg squared is the other leg. Square root of 2x plus 1. And now, in 3, you evaluate using the triangle. Evaluate by this triangle. I want a cosine the arc sine x over x plus 1. But because I made theta the arc sine, this is just cosine theta. Cosine is adjacent over hypotenuse, right? Adjacent, I computed is square root of 2x plus 1. Hypotenuse is x plus 1. There it is exactly. It doesn't matter what x is, that's exactly the result, as long as arc sine is defined for that thing. So it has to be a number between x over x plus 1 has to be between plus and minus 1, and this will be the cosine of the arc sine of x over x plus 1, always. How about that? Who would ever think, you know, you take a trig function, inverse trig function, it must be really complicated. It always comes out to be some nice algebraic expression in terms of roots. Sometimes the root isn't even there. All right, so that was the hard one. If that scares you, don't worry. Just be able to do that one and the other one. Okay, bring up any more questions you want to look at for tomorrow? Bring them at the beginning tomorrow too, if you want.
Yeah, probably will.
Okay, or have an office hour after class, you're welcome to actually do it also, so. Sometimes, you know, that old adage holds, every question brings up 2 new questions, so now that you got 6 more questions, now I presented 3. So we'll see. That's true in mathematics a lot. Every time you answer a question, say, well, what about, you know, there's some truth in that. All right, well, today we want to try and complete the section that won't be on the test at the quiz. It'll be on next week's quiz, and it'll be probably the hard part of next week's quiz. Well, this is not for this quiz. We did something here. We skipped ahead to section 7.5, and we're going to come back to 7.1 through 7.4. 7.5 uses these inverse trig functions immediately. This is continued. We started this yesterday. We said this, we're going to break this up into building blocks. You build higher and higher problems to solve one. We said, suppose we want to solve trig function equals a number. I abbreviate for trigonometric function. How do I solve that? Trigonometric function equals a number. Remember, like, inverse function, I'll give you one answer always. We want to find all solutions. I'll say use the unit circle. Again. So I thought any of the quiz things are in doubt, just draw the unit circle, maybe you'll get part credit. so use the unit circle. And then draw. So for example, but seriously, that's how a lot of people get stuck. I keep telling my classes that, you know, do all these homework problems. And, yeah, I can do that one. I can do that one. And you think you're ready for the test, and you come up to the test, you get 0 on all these things because you couldn't remember which method went with which problem. You got to be able to look at the problem and say, oh, it's this kind of problem. I use this method. If you see trig function equals a number, you go to the unit circle, right? So suppose I wanted to solve sine theta equals minus a half. How about that? How can I solve sine theta equal that number? Trig function equal number. I say sine theta is the y coordinate. I draw all points for which the y coordinate is this value minus a half. So it's halfway down here to the minus 1. I like that. And then I find out there's, in this case, 2 points on the unit circle. So there's one here. On here, there's exactly 2 terminal rays as a result. And now, any angle that goes to one of those terminal rays is a solution. So how do I find out what angles those are? I drop a perpendicular on either one of these. Let's say on this one. Since this one from y equals minus a half to y equals 0, here, this side must be length a half, right? This side is 1 because it's a unit circle. I recognize that triangle, right? These are two sides of a 30, 60, 90 triangle. The angle here must be 30 degrees, pi over 6. If I ask you to solve it in radians, then you immediately say the answer is theta equals pi over 6. Or what else? That's one solution. What's this other angle over here? Because now we're saying I didn't put any restriction on the angle. All right, I said, right, when I say find the arc sine, there's only one answer. But when I say solve sine equal a number, there's actually an infinite number of answers. One of them is the arc sine. That's this one here. But there's another answer right here. What angle is that? What's symmetry in these cases, right? If this is pi over 6, what's this one? Yeah, same one, right? By symmetry. This goes down to half, this goes down to half, right? So as always symmetry, you get two congruent triangles, triangles of the same measures on the other side. That makes this angle here pi plus pi over 6. Must be 7 pi over 6, right? This look familiar what we're doing? Hopefully. We did this last time. And so the other angle is 7 pi over 6, but we're still not done. Why not? As I said, I'm going to kill myself. I'm going to follow this and break my ankle. I'll get comic relief and then I'll have to finish. All right. All right. What are all angles? Check this thing. All right. All angles are all. You have a solution if and only if it has one of these terminal rays. So all solutions are the angles that are coterminal with these two that we found. So it's this one plus k times 2 pi, k rotations, or this one plus k times 2 pi. But we don't usually write it this way. The mathematical full pi, you're supposed to put the k after the 2. So you put a 2k pi. K rotations, whole rotations plus or minus. There's all solutions. Now, if I said all solutions in one rotation, 0 to 2 pi, then you just put these two. But if I don't say 0 to 2 pi, then I have to put all of these, where k tacitly is assumed to be any integer. That's a number with nothing after the decimal point. Infinite list. Infinite number of times you can rotate. There's how you solve. This is not on this quiz. Don't study this for tomorrow. Study this over weekend. Tell you with 4 days off, you guys will be training a bit for some math to do, right? Yeah, no class on Monday or on Friday as usual. All right, so there's all the answers to that one. Then we said, for a multiple angle in the trig equation, make a substitution. Substitute u equal the multiple angle. I'll do another one by example. We did this last time again, but this is some of the hardest material of the semester, I think. So I'll make sure we do a good job with it, right? And plus, I want to extend it a little. And if once you sleep on this, it's hard to pick up where you left off. So, pardon me if I repeat a little bit, but. Suppose I wanted to solve tangent of 2 theta equals square root 3. How about that? How do I solve that one? When you see a double angle or any multiple of an angle, the first thing you do is let u be that multiple angle, 2 theta in this case, to get a single angle. Then you go back to step one, right? It's the house that Jack built. Tangent of u equals square root of 3. Go to method one. How do I solve tangent u equals square root of 3? Here's what I do. I say tangent u square root of 3 can be written as a ratio square root of 3 over 1. And now if I divide top and bottom by the root sum square of those numbers, square root of square root 3 squared plus 1 squared, it'll make a ratio of numbers on the unit circle. This is 2. So I'll divide top and bottom by 2. Or you just memorize, wait a minute, I really don't want square root of 3, I want square root of 3 over 2. I really don't want 1, I want a half. So now this will be a ratio of points at the same angle on the unit circle, right? This was not in the unit circle, it's too far out. But this is the same direction, ratio of y to x, but one on the unit circle. And now there's one more possibility. What else could it be besides this ratio? Yeah, there you go. I'd be minus square root of 3 over 2 over minus a half. So this could be y and this could be x. It'd be on the unit circle with this ratio. Or this could be y and this could be x and be on the unit circle with this ratio. So I'm going to sketch the unit circle. This. All right, now at step one, when you have trig function equals a number, sketch the unit circle.